We'll conclude Module 1 with this video lecture in which we consider the birth of cognitive psychology. We'll look at how advances in human engineering resulting from World War I contributed to the early shift from behaviorism to cognitive psychology. We'll consider how communications theory and the development of information theory also contributed to the shift to cognitive psychology. And finally, we'll take a quick look at the timeline of the cognitive revolution. There were many advances during World War II that contributed to the shift from behaviorism to cognitive psychology. Probably most importantly were advances that were made in human engineering. During the war, countries were trying to develop better pilots. How do you build a better pilot? It turns out that this type of human engineering is best achieved using a mentalistic approach than a behavioral approach. There were also a number of soldiers who received brain damage during the war. These soldiers helped form the early damages to different cognitive processes. There were also advances made in communications, and the foundations for information theory were laid down during World War II. These ended up serving as a model for how cognitive processing works in the human. In fact, early models of human information processing referred to humans as simply human information processors. There was also the development of servomechanical devices, autopilots, and in the development of these devices, researchers often drew on expertise of psychologists who would attempt to understand how humans do something. So if you want to build an automatic pilot, you need to first consider what a human pilot is doing and try to develop a program that will do the same thing. It also tackled teleology. Teleology refers to behavior that is purposeful. Now this is important, of course, because purposeful behavior to the behaviorists was a type of mentalism. And so as far as behaviorists were concerned, there was no teleology in human behavior. Yet it turns out if you're building a servomechanical device, giving that device purposeful behavior, giving that device the ability to plan, actually works better than using something that's strictly responding to the stimuli that's being presented. If it works in a machine, why shouldn't it work in a human? And finally, there was the groundwork for the eventual development of the digital computer. And the digital computer plays an important role in cognitive psychology even today. First off, looking at artificial intelligence and running simulations. Both are tools that are used by cognitive psychologists and cognitive scientists. And of course, the computer itself is often used as an analogy to try to describe human information processes. As I mentioned, during World War I, researchers were trying to develop better pilots. And there were limits using contemporary behavioral psychology in how well you could build a pilot. Consider the following problem that was being observed in both Britain and the United States. Experienced pilots coming in for a landing at night began to manifest this very strange behavior. As they were approaching the runway, rather than slowing down and landing their plane, they would go to full throttle and nosedive into the tarmac. These were experienced pilots who had flown a variety of planes over their careers, and yet, for some reason, they were crashing their planes in a rather strange way. Now you could look at the behaviorists as they would try to explain this, but talking about motivation, responding to stimuli control of behavior, it really doesn't work. Those pilots were highly motivated to not crash their planes. This isn't a problem of motivation. It's some other issue. In fact, the problem itself was related to perception, judgment, decision-making, problem-solving, the types of cognitive tasks that we study in cognitive psychology. Fitz and Jones did an analysis in the late 1940s. They were interested in looking at pilot errors. They had actually determined that 50% of pilot errors involved misusing controls, like the pilot going to full throttle and crashing into the tarmac. So what they decided to do was to do an analysis comparing the different arrangements of position of control. So for example, there were usually three main levers that a pilot could reach for. In the B-25, the left was the throttle, the center one was the prop, and the right lever was the mixture. If that pilot ended up flying a C-47, that prop moved from the center to the left, the throttle moved from the left to the center, and the right remained a mixture. If they then flew a C-82, the mixture would move to the left, the throttle would stay at the center, and the prop would move to the right. The mappings between the control dials and the aircraft were not consistent. The mappings were ambiguous. They actually estimated that in the first 2 years of combat, over 2,000 multi-engine U.S. aircraft crashed because the landing gear and wing flap controls could not be discriminated from one another by location, feel, or movement. In other words, as the pilots were coming in at night, they would reach down and try to find their landing gear. But their landing gear was located directly next to the throttle. So instead of dropping their landing gear, they would go to full throttle and crash into the tarmac. The problem was a design problem. It wasn't pilot error at all. It was just simply that the aircraft were not being designed properly. So from human engineering, cognitive psychology developed this human-machine concept, or in the day they called it the man-machine concept. The idea that the pilot is actually part of the machine. It receives information from the external environment. She then processes that information and then operates in response to that processing. So in a sense, that plane does not fly without the human. The human is part of the system. If you're developing a servo mechanism, an autopilot, you merely take the human out and you insert a program instead. So interest began to develop in how does this pilot's programming work? Right? If the human is part of the machine and it's the programming part of the machine, to understand that, you really do need to take a mentalistic approach. Behaviorism isn't going to help you improve your pilot's operation because you're going to avoid studying this really essential part, the mentalistic part, the cognitive processing that's happening. And so for human engineers, you see humans as being receivers, processors, and transmitters of information, part of that human-machine system. And as receivers, processors, and transmitters of information, they have a mental activity that is worth studying. Also during World War II, as I mentioned earlier, there were advances in communications engineering. Probably one of the most important contributions was made by Claude Shannon. He was studying as a master's student, studying information theory. Claude Shannon is known as the father of information theory. He wrote his master's thesis, which was titled A Symbolic Analysis of Relay and Switching Circuits, in 1938. It would probably go unnoticed by most people, but Howard Gardner describes it in his book on the history of the cognitive revolution as the most important master's thesis of the 20th century. And it probably was. It was in that thesis that Shannon introduced the concept of a bit. As you know, our modern computers are built around the concept of a bit. So without this very important thesis, we probably wouldn't have computers today. In 1948, there was an important symposium held known as the Hickson Symposium. It was titled Cerebral Mechanisms in Behavior. Now, 1948, you are really still in a behaviorist period in North America, so a lot of the talks that happened at the Hickson Symposium probably highlight the anomalies that were starting to develop in trying to describe human psychology with this very simplistic stimulus-response psychology. There were several very prominent speakers, most of them not psychologists. Nevertheless, they were becoming interested in psychology. For example, John von Neumann gave a talk. You might know him as the mathematician who made some of the most important contributions, mathematically speaking, to the Manhattan Project, the development of the first atomic bomb. His talk was called Comparison of the Electronic Computer to the Brain. Right? So he actually drew this first analogy of how this new thing, the modern digital computer, electronic computer, and how it might operate in a similar way to the human brain. Warren McCullough presented a paper called Why the Mind is in the Head. Obviously, this is a very mentalistic paper. McCullough compared the nervous system to logical circuits, the kinds of circuits you might see in a large switchboard. Carl Lashley, we talked about him in the last video lecture. He supervised D.O. Hebb's PhD thesis. He was a behaviorist, but at this symposium, he was beginning to have some doubts. He presented a paper called The Problem of Serial Order in Behavior. In this talk, he argued that behavioral sequences, complex behavioral sequences, like language, are not simple chains of stimuli and responses, that the only way these things can work is to have centralized plans. Centralized plans are a concept that would be considered mentalistic by Lashley's early training as a behaviorist. There were other conferences as well. There were conferences on artificial intelligence, including McCarthy's Summer Research Project on Artificial Intelligence that happened in 1956. At this particular conference, Newell and Simon presented what they called the logic theorist. This was a computer simulation of human problem solving, one of the first simulations of human cognitive processes. George Miller is a cognitive psychologist who was very active during this time of shifting from behaviorism to cognitive psychology. He's recounted his recollections in a paper that I've included on your reading list. You should read Miller's paper. It's a short and interesting inside look at this shift from behaviorism to cognitive psychology. But he considers the birth date of cognitive science as being in 1956. Miller saw cognitive science as a counter-revolution. That is, it wasn't so much a scientific revolution that occurred because of an accumulation of anomalies, but rather a counter-revolution to the behaviorist revolution that had already occurred. So I guess, like me, Miller tends to see not one but two revolutions happening during the 20th century. He places the birth date of cognitive science at September 11th, 1956. And in his paper, he argues that there were a number of key events in 1956 that lead him to suggest this year as the birth date of cognitive psychology. Bruner and colleagues published a book called A Study of Thinking. Tanner and Sweats used signal detection theory, which was a form of communications theory, and they applied it to perception. Miller himself had published a paper called The Magical Number 7. You might have ran across that paper in your introductory psychology course. He was measuring the span of short-term memory and consistently found this number 7 plus or minus 2 kept cropping up as the span for people's short-term memory, and he referred to the magical number 7 plus or minus 2 in this paper. Benjamin Whorf, who was an anthropological linguist, began to write on the effects of language on thought. Again, very mentalistic. There was a special interest group in information theory symposium as well held that year. That again had Newell and Simon back with their logic machine. Rochester had used a computer to test Hebb's cell assembly theory that we talked about last time. Remember, cells that fire together, wire together. Noam Chomsky has started to lay the foundations for his psycholinguistic textbook, Syntactic Structures. Again, a mentalistic approach to language. So if we look at the time course of this so-called revolution, we can start back with Tolman and his cognitive maps, the accumulation of some anomalies that behaviorism was having trouble dealing with. At the same time, we have the Hickson Symposium, where we have a number of people not usually considered part of experimental psychology, but rather people in communications, in computer science and mathematics, who are starting to talk about this parallel between this new ideas of computers and human information processing. We have the conferences at Dartmouth in 1956, Skinner's attempt to explain language in 1957 in his verbal behavior textbook, and then just a couple years later, Chomsky's biting criticism, a review of B.F. Skinner's verbal behavior appeared. Miller was involved in establishing the Harvard Center for Cognitive Studies in 1960, and then, according to this graphic from your textbook, in 1967, Neisser's first cognitive psychology textbook. Of course, we know that wasn't actually the first cognitive psychology textbook. We talked about that in our first video lecture. Thomas More wrote the first cognitive psychology textbook in 1939. Interestingly enough, Ulrich Neisser was once asked about this textbook, if he was familiar with it, and he said he didn't. At the time he wrote his cognitive psychology textbook, he was completely unaware of More's textbook. In fact, he said if he had known about More's textbook, he would have called his textbook something else. And so you might not be taking a course in cognitive psychology right now if Neisser had been aware of that earlier textbook. I don't know what he would have called it. But in many ways, that 1967 date, I think, is important to cognitive psychology because it sort of marks the beginning of courses in cognitive psychology. Very much, I think, cognitive psychology is a product of the 60s, right, with that textbook in 1967. And that may be why there's a tendency for cognitive psychologists to think of themselves as revolutionaries. It was kind of a revolutionary time, the 1960s, protesting the war in Vietnam, flower power, and so forth. But if we actually think about this time course, we can see that there's actually a good 20 years of activity that's happening here. The scientific revolution would probably have been much quicker when you realize that your paradigm is not working properly. It's typically in science that paradigm would be shifted very quickly. So cognitive psychology in many ways probably still doesn't fit that definition of a revolution, simply because it's kind of a gradual shift that's happening away from behaviorism towards mentalism. That concludes Module 1, and our next module we'll look at some of the basics of cognitive neuroscience that's used in contemporary cognitive psychology.